I would like to introduce Tiago Ribeiro. So Tiago is a senior research engineer and animation scientist at Soul Machines. He did his PhD at Instituto Superior Técnico in Lisbon, where he collaborated internationally in many different European Union research projects and also some universities in the States, and focused mostly on multimodal expression in autonomous social robots. He also contributed to several book chapters in emotional modeling, social robot characterization, and robot animation. And he also published in several important conferences such as HRI, SIGGRAPH, IVA, ACMI. And today he's going to be talking about his work about autonomous animation of virtual and robotic characters. So Tiago, when you're ready, take it away.
Yep, thank you. So hi everyone, welcome to this talk. Thank you for being here, and thank you for the organizers for doing this incredible job. My talk is going to be split in two parts. One is going to be about the work that I did during my PhD on robot animation, and then there's going to be a brief presentation about what we do at Soul Machines, namely how we perform research on autonomous animation. So I always like to start my talks with the sentence that robot animation isn't just about motion. It's about, when I think about animation for robots, it's more about what we're communicating through the motion, and not just the motion per se. And therefore, it led me to define robot animation as both the workflow and the processes that give the robot the ability of expressing identity, emotion, and intentional reasoning during autonomous interaction with human users. Now, it doesn't just mean that we have these three key concepts here and we can just implement them. It actually works with all of them connected. So during an autonomous interaction with human users, we have autonomous behavior, and all of those are meant to express an intention, and there's a reason for all of those behaviors. Those intentions can be linked with emotions, the personality, or the motivation and the story of the robot character, as I like to call them. I previously presented the principles of robot animation. They are based on Disney's own principles of animation, and I discussed how they can be adapted or not to robots. If you want to read more about them, I'm not going to spend time talking through them. I recommend looking at the most updated publications because I have revised them compared to the original one from 2012. In order to support robot animation, I worked on, I and GAIPS and more people in the lab have developed the SERA. It's a robotics architecture based on SIGGRAPH, which you might know from the IVA community. And it puts the control of the robot in these three layers, where we have the decision making at the highest level. Then we have behavior management, which includes action selection, resource management, synchronization, and things like that. And then we actually realize it on the multimedia application, the text speech, the animation engine, and all with information that also comes from the world and from the user as perception. This architecture has been used in GAIPS and is still used today, I think, on various different robots and on various different applications. And it allowed us to reuse a lot of different pieces of the system with them. Now, the most important part for me is actually the animation engine. That is where I focused my research and my PhD. And on that, I'm going to just jump directly into Nutty Tracks, which is a symbolic real-time animation system that I developed that is both used as a design environment and as a runtime environment to support interactive procedural animation. And it can be used on, it is embodiment agnostic, so it can be used on any robotic character or a virtual character, doesn't really care. And also, I tried to also provide some kind of link to animation tools that are commonly used by professional animators and artists. Namely, Nutty Tracks, which you see down here below, was heavily inspired by the Unreal Engine's material editor, which you might know of. I also made sure that there was a plugin for 3ds Max, which I was familiar with at the time, to allow to perform a more artistic kind of animation, animation process to design the expressivity. So you can see it, one of the earliest videos actually in action here. So you have a representation of the robot in 3ds Max, which is a professional animation software. You can use all those tools that you already know of and see them directly on the robot. This is just the design part. Then when it runs, it offers this environment which we can just connect boxes and compose animation. And this is not really like, for example, choreographer, which is used by now robots, where you program like a state machine. This is actually a program that runs on each frame and produces a new piece of the signal at a high rate. So how does it work under the hood? What NuttyTracks introduces is the Nutty pipeline. Basically, it is inspired on the OpenGL shader pipeline, if you are familiar with it, which basically takes, when you have a 3D scene, you have vertices, lights, cameras, and you take all that information, you process it using shader programs, and you produce pixels. Now, in this case, we're taking parameters that arrive from wherever. It can be the AI perception or control panel for Wizard of Oz, for example. And all those parameters are processed, go into this animation processing unit, which applies them to an animation program, which works a bit like if it were a shader program, and then outputs an animation frame or even just a partial one based on that embodiment and output that we specified. And this runs as a cycle using an animation clock, can be between 30, 50 times per second, whatever is required. It's important to know the difference between embodiment and output here. Embodiment specifies what is the structure of the character, like the skeleton and what elements can be animated. The output is, where is this sent through? Is it an Arduino? Is it a ROS? Is it a USB interface? Is it actually just a WebSocket because it's controlling a virtual character? So embodiments and outputs are two separate things here. Within this pipeline, I'm going to go deeper into this animation processing unit. Now, this is at the core of NuttyTracks, and I explain this as different levels which can be evolving. So if you think about a level 0 APU, what does this mean? It means that you have some kind of inputs, which may be float parameters, for example, in an animation block, which basically contains operations that are applied to those parameters, and then you produce an output. And this can run on each frame, and that is a level 0 APU. When you add a sequence of blocks and each block takes different parameters and they compose to each other, then that becomes a level 1 APU. So you can have more complex animation programs processing your motion. Now, it really becomes more interesting when you get to level 2 APU, APU where you have the multi-layer system. So you can have different layers producing their motion independently, and then they all are composed together using some kind of blending operation, which can be additive, overriding, whatever you think is best. And then that goes into the output. And finally, the level 3 APU is a multi-stage one. So you take that previous level 2 APU, but then you add post-processing stages to it. And these post-processors may be, for example, IK, which might take the result of these blending operations, but then it's going to override the control of it, or path planning, or other kinds of filtering that you may want. So NuttyTracks was built as a level 3 APU. So you have this first stage, you take in a Nutty animation program or an app. You feed it a body model which specifies what robot is this. Is it an Emis, an Adelino, an Al, Baxter? I don't know. It receives information like when I implemented it was using Thalamus as an integration framework. We could replace this for ROS or some other integration framework which changes these commands, these messages, and runs inverse kinematics and then emotion filter, and then finally goes into the output. Now I'm going to focus on two components here. This the Nutty motion filter and the inverse kinematics. And this Nutty motion filter is basically an inertialization predictor filter. It's a very important piece of the system because You can think of it as a Kalman filter, for example, except that it provides a more initializable character. And you can basically set parameters to make it smoother and feel heavier, or very responsive and lighter. What it does is it can take this discrete input or a C0 signal and transform it into C1 to C3 continuous output signal on a per frame filtering. So it requires no look ahead to perform this. It was actually initially developed for motion trajectory processing and filtering. So in this case, you see an example where this dark sphere is the new target set point for the white torus not to follow. And it's using the filter to actually create the whole trajectory in real time. And as I switch parameters here, you can see that the motion changes, and it can be smoother and slower or faster, and even have some kind of oscillation. It depends on what you need and what you want to convey. I don't have a video showing it directly, but it is also used, for example, on joints. If instead of taking the X coordinate, for example, as you see here, which is just a one-dimensional filter being applied, you can also apply it to an angle, which is controlling the joint. And that's what we also use, as I'll show later. Now, in terms of inverse kinematics, I created ERIC, the expressive robotics inverse kinematics technique, to address the fact that first I designed and built Adelino. And Adelino is a craft robot, which I designed to be very abstract and nonverbal. And I wanted to be able to convey motion through it mostly procedurally. The problem was that after I designed it and linked it with nutty tracks, I wasn't really able to control it without IK. So I had to develop ERIC in order to be able to provide an expressive control over this manipulator-like robot. So what ERIC does, I'm going to skip a bit ahead here. It allows us to track a person just like you would track with a manipulator if you just set the endpoint to gaze at a person using because it works as its head. But at the same time, we can control the actual posture of the body while it is tracking the person's face. So it is a bit jittery, but the thing is, does the message get conveyed? Does it manage to communicate this posture as an intention? This is pretty much the same thing, except it's not facing forward. Now it's turning to the side, and that makes it a lot more difficult. Adelino, I have one right over here, it actually uses hobby servo motors, and it can only rotate 9 degrees to each side, which makes it also quite difficult to control for. So after we saw this, it seems great, but does it actually solve properly? Can it really aim at the given orientation correctly? And how much does it have to alienate the given target posture in order to do this? And additionally, is it actually useful? Can we use it in HRI to communicate thought and intention? So I took a brute force approach to evaluate ERIC algorithmically. Basically, I ran it across various different embodiments across a huge number of postures aiming at different orientations. And because I knew what I was asking for, I got a result back, and I used that to calculate a combined error, which is basically how far away was it from the target orientation, and how far away was the shape, the posture shape, compared to the one that I gave first. This is a weighted sum, sorry, of two errors actually, the orientation and the posture, because the orientation is more important. I want the character to follow the person, even if it has to alienate the posture a bit. I also compared it to DLS, which is a very commonly used Jacobian-based method, which I'll show later. So I tried it on these embodiments. Immediately I removed the A version because it's too simple and pointless. Adelino matches the C version, which is the one that I also compared to DLS. And for each of these embodiments, I used tons of different postures and a lot of different orientations. So for example, for the Adelino-like robot, we had over 3,700 postures and over 7,600 orientations, which amounted to almost 30 million samples that were simulated. In total, I ran almost 365 million samples, and obviously I had to use a supercomputer to do that. Now, the results from this evaluation were actually quite in line with what we were hoping for. We can see the combined error on the top, the orientation error on the middle, and the posture error down below. Now I'm going to break it down first here. The orientation for each of the different embodiments was quite good and below the threshold, which was something that I defined as it's good enough. I tried it empirically and thought, if I use this 0.04 as a threshold, it works pretty fine. So regardless of the embodiment, they were all mostly over there. When we look at the posture, because the orientation was more important than the posture, then as we remove degrees of freedom, so for example, for the red one, we get much more and much higher errors on the posture measure. And as we add more degrees of freedom, like in the pink one, we reduce those. So it means that the algorithm is holding the orientation and is having to distort the given posture in order to keep that orientation. And that's good. That is exactly what we wanted. The combined error ends up looking like this. So as we have more degrees of freedom, it works better. Now, in terms of user studies, I had two scenarios. The question was, can ERIC provide Adelina with the ability to communicate nonverbal hints to a user about what action to take next during a particular task, and obviously while also conveying the illusion of life. So first, I developed the Ahoy scenario. I've presented this before. I'm not sure if you've seen it. It's a pantomiming game. So the robot performs an animation and participants have to guess what it was, like if you're playing pantomime. So we would play it, then the players would guess, and then if they got it correct, the robot would say yes, or it would say no. There are 7 different animations. Maybe I can show them all later, but I'm going to skip ahead to save some time. There are 2 study conditions. There's an intention expressive and a non-intention expressive. On the first condition, when the robot, after the robot plays the animation and the user starts guessing, depending on if the guess is near or far away from the real one, it is considered warm or cold. And if it's warm, the robot takes a positive posture. If it's cold, it takes a negative posture. And that is supposed to give a hint to the user about how close they are to the right answer. In C2, it does not. It just holds the same neutral position, so they have no hint. And yeah, I'm not going to detail the results. It's already been published and presented, but the robot did convey the illusion of life, and players did perceive the robot's posture changes as its intention of providing hints in C1. However, there was a major flaw on the design, which was while the players are guessing, they're standing still. And so all the hypotheses I said actually were verified, but I'm not really challenging the orientation tracking because they're always standing in front of the robot. So this wasn't really So I developed a new scenario, and this is unpublished work. I've only presented during my PhD thesis defense, and I have tried to publish it a couple of times, and for some reason it always came back. So I decided today that I'm just going to release it on archive, and you can already visit my website or follow this QR code if you want to read it. It's called Avanzati, so it follows a very similar structure, but now we introduce a floor piano to the activity, and the players have to interact through this floor piano, and this really forces them to move around, and therefore I am actually validating this with the changing orientation of the target. So the idea of the game is that there's a sequence of notes that the players have to guess, and they do this just through trial and error. They try to play a key with their foot, and the robot says yes or no. Actually, it only says yes when they get it right. Otherwise, they just keep on trying until it works. However, again, there are conditions. There are 2 enhanced conditions, and one control condition. On the enhanced condition, again, as the players tap the keys to make the guesses, if they are warm and going towards the right key, then the robot will take a positive posture. If they are moving away from the right key, then it is going to take a negative posture. On control, it does not. It always holds the neutral pose. So the whole game structure works exactly the same, except that they don't get any hints. The difference between LIREC and EBPS is that EBPS is an example-based posture synthesis. So I had to create a tons of postures for each version, neutral, hot, warm, and cold, towards different orientations, and then it uses an interpolation model. Basically, it mimics the behavior of LIREC, except that it requires a lot of authoring. And I just wanted to be able to compare these two. So here's an example of a gameplay in Avanzati. Oh. Sorry, I think there were some bumps here. So this is in the Sierra condition. So the robot is providing hints. And the participant is trying to follow them in order to find the right key. Okay, great. Now, she really understood how to communicate with the robot. That is a real HRI. Oh, and this is all fully autonomously from start to the end of the activity. I'm going to skip a bit ahead. The EBPS, if you watched it, it would look quite similar to that. I'm also going to show you what happens in the control version where there are no hints. So the participant just has to keep on trying until they get it correct. And that can become quite frustrating. So this is very bad HRI. Oof. Okay. Forward. Just gonna. Okay. So my first hypothesis was that in C control, players were going to commit much more mistakes than in LIREC and EBPS. You can see the aggregation of EBPS and LIREC as blue here in the enhanced condition. And yes, we did have a lot more errors. So using LIREC allowed players to just perform more directly and commit less mistakes. Players in LIREC will play as well as in EBPS. It was important because I wanted to make sure that LIREC could perform as well as a highly tailored alternative technique. And yet it performed pretty much the same. So there weren't any relevant differences. Subjectively, the robot was perceived to convey the illusion of life in all conditions. Even though there was a drop, we can consider that they were all well above the median. And so that was okay. It was obviously less, it was perceived as conveying the illusion of life less in controlled condition because it wasn't so expressive with all that posture shifting. So that was also expected. And the players were able to perceive the robot's intention and motivation as being towards helping them in both the enhanced conditions compared to control. And that was quite obvious. And that was the most important finding here. Also, the robot was perceived to understand and play the game well in all the conditions, which was also important to make sure there wasn't any biasing happening on there. And so this was the end of the first part on the robot animation. I'm going to move into a brief overview about soul machines and how we develop autonomous digital people. We are aiming both at today's digital businesses and applications, soul machines, but also at the future when we look into the metaverse and even Web3. We take a biologically inspired approach and develop cognitive architectures of interconnected neural networks that can interact and sense and learn in real time And this behavior, this embodied intelligence is all driven through a digital nervous system, which controls a virtual body. So I'm actually going to show a video for a while about it because it's better to show than tell in this case. And then I'm going to talk about some of the aspects of it.
Hi there. I'm Sam, your guide to Soul Machines. How are you doing?
Soul Machines is an autonomous animation company that has built the world's first digital brain. It enables human-like face-to-face interactions that are personal, empathetic, and interactive in exactly the same way that our human brain animates us and brings us to life when we interact with each other.
So what's important about this human operating system is it providing a connection between artificial intelligence and people, but even more importantly, it's creating this connection between people and artificial intelligence. So as we explore the potential for this, people can put this technology to work in a way that redefines their business, redefines what is possible for their customers, for their clients, for their industry. And we're moving into an era where we're going to spend more and more of our time interacting with artificial intelligence, with robots and other forms of automated machinery. And the core concept behind what we do and the technology we deliver is, wouldn't all of those machines be more useful to us as humans if they were more like us? Literally.
Oh, sorry. Just move back. Okay, but I think the message was sort of conveyed. So at Soul Machines, let me just switch the video mode. Okay. At Soul Machines, we're developing autonomous digital people, and these are hyper-realistic both in their appearance, but also in their behavior, such as eye contact, their facial expression, their body language, and the behavior within a certain scene or context. This is all powered by the Soul Machines Human OS, which is a cloud-based platform which supports our digital brain and its autonomous animation engine. But it's not just our proprietary system, there's a lot of third-party tech also in there, obviously. Now, to give you an idea of the company profile, we have top talent from all over the world. We have over 200 employees, which includes 5 professors, 19 PhDs, and even 3 Academy Awards. We have offices in a lot of major cities and are backed by some of the leading AI venture capitals. We have a lot of different partners with whom we work with, not only on developing the technology and integrating it, but also on finding applications for it. So besides the clients, we have clients and partners at the same time. Now, going back into the autonomous animation idea, well, at Soul Machines, we define autonomous animation as the process that enables an embodied agent to behave in a contextually appropriate manner with minimal human direction. And it's important to say minimal human direction because we don't just want it to be so autonomous that it has no human direction. We always want to have at least some direction to provide it. And we have been developing these levels of autonomous animation, which are the 6 levels. And we split these into pre-recorded animation and dynamically generated animation. So the level 0 of autonomy is that you have an animation that is just pre-designed, and it can be like an animation playing a loop and never changes. You can have motion capture animation in which you may be driving the animation in real time, so you can change it, but it requires you to recapture it every time you want to do that change. On a scripted animation system, you can define what direction it's going to take and how it's going to transition, so you can think of it as like a decision tree or dialogue tree, but it's still tied to that script. So if you want to change the content, where content includes the speech, then you have to change and reauthor the whole thing. Now, going into the dynamically generated animations, and this is where we are focusing on, a guided autonomous animation system is able to incorporate the changes to the content without requiring reauthoring. So that means that, for example, if you give it a text to speak, it will be able to generate all the gestures automatically in real time and do it synchronously. So you don't have to reauthor it. You can just change the content. You can change where things are. If it's pointing at something on the screen, it will just follow that object. It's not prescripted. As we move forward, a goal-based autonomous animation system allows us to establish goals, and those goals will define the content. So it is a bit higher level in terms of autonomy. And finally, a value-based system is even more autonomous. And the best way to think about it is, if you say, for example, a nonprofit organization that provides medical services in remote, underserved areas can deploy a virtual nurse. And that virtual nurse would be a level 5 autonomous animation system, capable of providing customized advice depending on the patient's input. So it would have to be able to define the goals, and based on those goals, define the actions that it's going to take and the content that it's going to use for its performance. Now, working at a company like this means that we keep on juggling this balance between looking at the business and product side, and also the tech development and R&D. So in terms of the business, we set this as a roadmap and goals in thinking about delivering to clients. I personally work on the R&D and the tech development part. I normally do not have much contact with the business or the product directly. Instead, what we do is, based on what we get from that roadmap, we create new technology, solve new problems, and face these challenges by performing research and development. And then we feed that into the product, which is then going to be delivered to the clients. At the same time, obviously, we are the ones who know how it works. So we also need to support the product whenever it's required. We are conducting research in this embodied AI space, and therefore we constructed a modular architecture. And this allows us to implement various models as they evolve. Because this is a very rapidly changing field, as you all know, we have brought a version of this current project to the market. And as we keep on evolving the models and working with a broader ecosystem, our commercial products also get updated. In terms of this modular architecture, we support 3 types of systems, basically proprietary systems that we develop internally, a lot of open source systems as we can, and also third-party proprietary systems. And the balance between these will depend on the needs and the features, and also what the clients want. There are some examples of some third-party systems you might know and also use. We're not just limited to those. There's a lot more that we are using and will keep on using in the future, because this is ever evolving. We also produce quite some scientific matter. We've released over 25 publications in various different conferences, including HRI and SIGGRAPH, and also journals. And we also produce, obviously, patents. We produce over 14 at the moment, and several pending ones. Now, going to the final track of this presentation, just going to give you an overview about Baby X's brain. And you might have seen or heard about Baby X. It is our developmental prototype, designed both as a standalone research project, but also as an expandable base that we feed into the commercial product. So we use it to explore new features that we can then deliver into the commercial product. The goal of Baby X is to explore human cooperation with machines and the foundations for creating a digital consciousness. Some of the key functions that we have and explore and research on the brain, for example, decision-making and planning, the motor system, the somatosensory system, the multimodal association, perception and imagination, visual system, auditory system, neuromodulation, emotional system, language, behavior, memory, and learning. And to make it just a bit more technical, or something that you might also relate with, here's basically some of the key fields that we actually actively develop on. And these are grouped into these 5 major categories, which we define as emotion, action, perception, cognition, emotion, and metacognition. This categorization is a bit debatable. I know you can consider that emotion is a cognitive process, but this just allows us to split these into different types of categories. Within all of these, I work on some of them, definitely not all of them, and that's how we tend to work throughout the company. Now, I have just one final video, and this is my last slide if I have time. It's almost 2 minutes, and it shows you what happens within Baby X. I'm just going to play that, and then we'll move.
Baby X.
This is Baby X, so she's basically an autonomously animated virtual infant. All of her behaviors are generated on the fly by neural networks running live, and so she's seeing me and listening to me and responding to what I do. So she's going to start wondering what I'm doing and starting to get upset because I'm not paying attention to her. So I need to calm her down, but I have to talk to her like a real baby. It's okay. Hey.
Baby X is driven by a virtual nervous system. So let's take a look at what that actually means.
What we're looking at here is Baby X's virtual anatomy, which is all controlled by her virtual nervous system. So that's controlling everything that she's looking at, all of her expressions. It's even controlling her breathing rate and her heartbeat. We can make it more transparent, and we can zoom out and see the whole model. All of the motion that you're looking at is controlled essentially by her brain model, which is driving her limbs, her facial expressions. We can see the facial nerves through here. Let's take another level deeper, and you can see her virtual brain model here. You see the brainstem, which is basically responding to all kinds of sensory input, and it's affecting the attention of the model.
Baby X can also interact with a virtual web page.
This is what she's looking at here. So she's trying to draw a heart.
And her creative abilities are surprising.
Let's play some piano of Baby X. I can interact with her too. Good girl, okay.
Okay, so that is it. Thanks.
Thank you, Tiago, for your presentation. It was wonderful to see the evolution of your work, as well as a bit of your experience in industry. I think that's very relevant for the Talking Robotics community. So I would like to open the session for Q&A. So if you have any questions, please raise your hand in the chat or write it down in the chat as you wish. So let me do one first warm-up question for the audience. And I'll start with something that's a bit more specific to the presentation that you had. So in the user study that you did with the pantomime, the Ahoy first one, how did you determine what was the distance to the correct answer? So you said warm and cold, but it was categorical. How do you do that?
So in that first one, we didn't have the ability to actually process what the users, the participants' guesses so well. So we had two wizards just listening directly the live feed of the audio. And there were two wizards in order to be able to respond as quick as possible. I think we had a latency of about 2 seconds, which allowed for the participant to say something. One of the wizards was listening and would say warm or cold, and the other one would click a button, depending on if it was warm or cold. So I basically transformed these two students into a computer, an organic computer. And that then triggered the actual expressive response. So it would be quick enough for interaction. And that's also one of the advantages of the Vansati scenario, is that assessing the answer was very quick. I was just processing the audio from the piano directly to see if it is the right note or not. So that became fully autonomous. There was no kind of wizard step involved.
Okay, thank you so much. I see a couple of hands in the air. Maybe I can give the floor first to Bahar. Bahar, go ahead.
Sure. Can you see me? Hi, Tiago. Nice to see you. Thanks for the great talk. I was brain.
Oh, I'm missing
so
that.
is there like what processes is it? Can you
I missed
hear me?
part of your question, sorry.
Oh, sorry. I was wondering about the neural architecture of the baby X. Is it rule-based? Is it like data-driven? Is it probabilistic? What's the like the memory structures and so on? If you're working on it?
It's a composition of a lot of different systems, and not just one. It's not just one neural network. I have no idea how many neural networks there are in there. It's actually hybrid. I don't really know how to give a concrete answer to that because I don't normally work directly on the Baby X project. I work more on the adult part of the animation system. But as far as what I know about it, and also what I know that can be said about it, is that there are several different systems, and that might contain some kind of rules. It will contain some kind of models, and they may be neural networks, they may be SVMs, they may be something else, but it's just everything working together. And in most cases, their outputs are just connected to each other's inputs, so that you have this network of networks.
I see, thank you. Is it ever possible to interact with it in the future?
It is not, I don't think it's available as a public demo. We have a public demo on our website on soulmachines.com, but it is an adult version, not Baby X exactly. Baby X normally is used by the furthest research that we have, and Mark normally presents it at conferences or demos it. I'm hoping that we can have a public demo soon, which I'm trying to organize too. And I'm hoping that's going to be in Europe.
Great. And one last question. Is it like, do you use life learning or like continuing learning approaches or developmental learning, for instance?
Sorry, there was a failure in the...
No worry, my internet connection is very unstable. Do you use lifelong or continuing learning or approaches?
Okay, I didn't get the whole question. I think do I use lifelong or continuous learning? As I said, I work on the autonomous animation part. I wanted to give you a brief idea about what happens at Soul Machine. I don't work on the development. I don't know how to answer that question. I don't want to give you a wrong answer, sorry. So a lot of what I actually do is still protected by IP, and I can't really reveal it. So the goal was that I give an overview of the various different fields that we address at Soul Machines. And it's not necessarily that I know all about them. So I understand your question. That's a quite interesting one. And I probably could answer it, but I don't want to, I don't think I'm the right person to give you the correct answer on it.
Okay, thank you.
Thank you.
Thank you so much. We have a lot of questions, so we need to move forward. So Ross, go ahead.
Sure. So I also have a lot of questions, but I'll stick to one, we'll say. First, great talk, buddy. Always love seeing you. Yeah, let's see. So your dissertation work primarily focused on animation systems for robots. I know you said Nutty Tracks could also be applied to virtual characters, but you were focusing on non-humanoid robots, and now with Soul Machines, you're working more with on-screen virtual characters, or at least from what we can tell, on-screen virtual characters that are more humanoid in nature. Could you just talk a bit about the fundamental differences in how you approach animation, well, dealing with physical non-humanoid systems versus virtual humanoid systems?
That question alone could lead to a whole new talk. So that's good. Yes. There's a lot of things in common and a lot of things that are different. So what's in common? What's in common is that even without being aware of those autonomous animation levels, Nutty Tracks was already a level 3 autonomous system based on the levels that are defined by soul machines. So that means it adapted to content. It wasn't pre-scripted, and it was all dynamically generated. So what's alike is that sense that there's some AI, there's a direction, there's content, and then we need to generate motion in real time towards it. There's no timeline, and the interaction cannot just be railed towards a certain direction. It has to be open to whatever the user is going to do. And my experience and my knowledge on that field was something very valuable that I brought along into soul machines. In terms of the animation per se, the mechanics, it's totally different, right? So first of all, when you're animating the 3D character, you can just throw quaternions at it, and it's never going to break or damage or harm you. So it ends up being much easier mathematically to deal with the systems when you're just using quaternions. Of course, there's a lot of things that you need to consider, like joint limits and things like that, but it ends up being easier. At the same time, it's also more complex, because if you have a robot and you get it to walk, then it's like, great job, here's prizes, and here's a PhD, and here's the lab. If you get a character to walk, you're going to hear like, oh, great, now can you get it to jump and fly and stand on one hand? Because we can't do all of that with 3D animations. And so the sky's the limit, and that means we try to do much more complex behaviors and much more complex and complete interactions than we do with typically with HRI.
And because you said one thing, I just want to elaborate on this just a little bit. You mentioned that Nutty Tracks is more like a level 3 kind of animation system. I was curious, in your timeline, it showed, I'm assuming the role of the animator, it listed them as author for, I believe, the first 4, then the last 2 said trainer. Could you talk a bit about the role of the animator in this autonomous animation process?
Well, when you're playing animations, even through just a rule-based system, what you have is you take animations as input, and then you play them out into the system. And you can play them out in very complex ways. You can actually compose them and trim them and perform time warping on them too. As you create a very elaborate system that can do all of that on the fly, you might still take information from animations as input, but you're typically not going to be performing the animation at any moment. It's always going to be something that is trained by the information that an animator may give, for example, to provide an idea or a guideline for motion, but then it's going to change depending on how the user is responding emotionally, or how the actual character's emotional model is driving it. And it can change the expressivity of it. And those changes are also provided by the animator. So when the animator is designing an animation, they know that it's not going to play faithfully. They know that it's just like a back line of what the animation is supposed to look like. And then it's going to be able to adapt to different emotional states, for example.
Thanks.
Thank you so much, Ross. We have time for one last question. Ian, you raise your hand, go ahead.
I was hoping I was also answering Ian's question with this.
So I can start my video. I should do that.
Okay.
Hey, so I guess you saw my question in the chat.
Oh, I lost the audio.
You did? Can you hear me now?
Yep.
Okay. I think Zoom likes to change my mic level for some reason. I don't understand. Can you hear me? Sort
On
of.
and off. Let's go.
Yeah, I'm watching it slowly decide that it wants to turn the level up as I speak. So that's why I'm saying a lot of words, to get it to be a collaborator with me. I enjoyed the part of your talk that I made it for. My question was about pre-animated gestures versus gestures created in real time, and you partially addressed that already in what you were saying. Because I have a follow-on question. You were just talking about how the animator gives a suggestion in the kind of animation, and then it can be changed by the system. And thinking in terms of numbers of variables that are changeable, what kinds of how many different sort of controls? What I'm imagining is that you've got an animation laid out in a graph editor, and you've got it in all these curves, and then theoretically those curves can be collapsed and expanded and maybe elevated and so on. I wonder just how many actual parameters there are that are available to the system to adjust that, if that is a real question.
It is a real question. I love that question. The only problem is about, so you might understand that as a company, we produce IP, and we cannot talk about the IP before it's produced. So I can only produce a paper and give a talk on the things that I did after it has been released. And I fear that the question you're asking might be slightly shadowed by that IP protection. So it is a great question. I hope that soon I will be able to talk about it more publicly, because I really want to, and I understand what you're going to. But that is more detailed than I think I can explain at the moment.
Okay, I wish I had a question that you could actually answer.
I'm sorry. That is also one of the things about doing research and trying to be connected with the academic community and being at a company, is how we juggle between these criteria. It takes us over 2 years to go from working on something, elaborating a patent, getting it published, and then being able to actually write a paper or do a presentation about it. And which is quite different than from what happens in academics.
Right.
So it's actually the first time that I'm being asked a question that I can't just give out.
Well, thank you in any case.
Okay. Thanks for the question. It was really good.
Thank you, Ian. And I think with this note, we can close the session. Once again, I would like to thank Tiago for hosting this session and for his presentation. And I would just like to take 2 more minutes of your time, just to once again share my screen to introduce the next week's, or in 2 weeks, speaker, which hopefully you can see my slides once again. Yes, hopefully you can see the slides. And in 2 weeks, we will have Sam Spalding from the MIT Media Lab. So you're not going to want to miss this session. And once again, we thank Tiago for doing this presentation. And we would like to thank also our sponsors, Animata and CMU, without whom this would not be possible. And having said that, we'll see you in 2 weeks. Thank you so much for attending today's session.